Okay, it's been a while since I've done actually. Well, I guess I've made a few um, videos, but I needed to really go over this idea of center of mass a little bit better with you all. Okay, so I've got three problems here of center of mass, and I'm putting these in the week 9 folder. These three things it'll be like the entire video series. This will probably take 5 or 6 little 4-minute videos for me to do to get it to work. But anyway, so we're going to calculate the velocity of the center mass of this system before the collision. This is almost identical to the hockey player problem that we did in class, and it's almost identical, but I want you to understand the velocity of the center of mass, okay? In that the velocity of the center of mass before a collision is equal to the velocity of the center of mass after the collision due to conservation momentum, as long as the net external forces in the problem after the collision are the same as they were before, or they cancel out and equal zero. The net eternal, in other words, everything's moving at a constant velocity again. In other words, if these two collide together, and because of the collision, this little particle here hits a button on the bigger particle that accelerates it, then the conservation momentum is not conserved because it's going to be moving. All right, so all I want to do is calculate the velocity of the center mass of this, and I'll break it down into its two components. All right, and you'll see that the velocity of the center of mass, uh, what we get for if you solve this for what's the final velocity, you'll see that that is actually the after the collision. You'll see that that's actually the velocity of the center of mass before the collision. All right. Okay. So let's take a look. So the velocity, so mass 1 in this problem, and we could also find the, but I just wanted to find the velocity of the center of mass. So mass 1 is 2 kilograms. Mass 2 was 4 kilograms. The initial velocity of 1 in the x direction is equal to 3 meters per second. The initial velocity of particle 2 in the x direction is equal to 0. It only has a y component before the collision. Let's get that out of the way. The initial velocity of 1 in the y direction is equal to 0, and the initial velocity of 2 in the y direction is equal to 5 meters per second. So we got a big object, a bigger object, moving at a smaller object, an object that's got twice the mass, moving to something at almost twice the speed. I think it's going to dominate this collision. But anyway, so let's find the velocity of the center of mass in the x direction. So what we do is we just look at the velocity of the center of mass in the x direction. And this is how you calculate the center of mass. I'll write out the formula. It'd be m(I) times v naught I, the sum of those, divided by the sums of the masses. Okay, and this is all in the x direction. Masses don't have a direction. So we've got 2 times 3 plus 4 times 0 divided by 6. Oh, this is nice. So we've got 6.0 kilograms meters per second up above divided by 6 kilograms down below. And so that comes out to 1.0 meters per second. And then the velocity of the center of mass in the y direction, same thing. Sum of the masses in the going in the y direction divided by the sum of the masses. The masses have spoken. No, sorry. All right, so m1 v naught in the y direction is 0 plus m2 times 5 divided by 6 kilograms again because the masses did not change. And so we've got 4 times 5 is 20 divided by 6, 20 kilograms meters per second divided by 6 kilograms. Aha! Kilograms cancel. 20 divided by 6, same thing as 10 divided by 3, which gives us 3.33 meters per second in the y direction. That's the velocity of the center mass in the y direction. And if you did this as a collision problem, the momentum before equals the momentum after, you would find out that the overall final velocity, so the velocity of the center mass is equal to 1 squared plus 3.33 squared and the square root of that. All right, out here on that one. Velocity of center mass. It's the same before collision as it is after. That was the big idea.